Let us discuss the covalent bond. A covalent bond is a chemical bond in which two or more electrons are shared by two atoms. A classic example is whenever you have hydrogen with one electron and another hydrogen with another electron, you can use fish hook arrows to demonstrate movement of two electrons to come to join. So those two electrons will be between the two hydrogens, and there is where you have your covalent bond. But you also have another type of covalent bonding where only one of the atoms provides the electrons. So for example, nitrogen can provide both electrons to an H+, which does not have electrons. He lost one electron. This time we use double-ended arrow because we are moving two electrons, and that would give this structure we call ammonium. The nitrogen will now have a plus form of charge. This hydrogen used to be this. This is the two electrons that are shared, provided by only the nitrogen, but that too is also a covalent bond. Now consider the fluorine atom. Each comes from main group 7A for sure, so you expect the Lewis structure of the atom to have 7 dots on the outside as shown. Now these two can combine again using fishhook arrows. Remember I said fishhook arrow shows one electron movement. So when those two electrons come together, they come in here and they are now shared between the two F's. And where they're sharing, we draw a line to show a covalent bond that was formed by sharing of electrons. The electrons that did not take part in bonding, they are called lone pairs because they are lonely. They are not bonded to any other element other than the element they are sitting on. So they are called lone pairs. If you look at the Lewis structure of water, you have two lone pairs of electrons and you have two shared ones. Let me use a different color, the red, to show you the shared electrons that give us the two bonds, and then the lone pairs will be out there. And really, if you look at the water by itself, it's gonna have this Mickey Mouse looking like knobs. Those are orbitals, and the molecular shape will be bent. When you connect hydrogen to oxygen to hydrogen, you get a V shape, right? We call that bent molecular geometry, because the electrons take much room, and electrons that are in the lone pairs, they repel the electrons that are in the bond, because both electrons in the lone pair in the bond and in the bonds are negatively charged. So according to valence and electron pair repulsion theory, we expect that the water is not going to be linear as suggested here. Instead, it's going to be bent because of repulsion of valence electrons. We'll talk about that soon in molecular geometry. There is also multiple bonds that can be formed by sharing, and you're looking at CO2. Okay, so CO2 will have two lone pairs on each oxygens on the sides, and there's a double bond in between them. So that means you expect 4 bonding electrons on the left side of the carbon and 4 on the right side of the carbon, and that will translate to a double bond on each side of the carbon, like that. So you have the lone pairs that did not take part in bonding. So these double bonds right here are actually also covalent bonds because they are made by sharing. You can also have a triple bond like you see in nitrogen, where in between here you have 6 shared electrons. Remember the rule, one bond is always equals to 2 electrons, and those electrons tend to be shared, which is why we're using the word co, like cooperate, colleague. When you say this is my colleague, that means you work together. So we call this covalent because they share valent electrons. They share valence electrons. Co, share, valence electrons, covalent. lengths of covalent bonds. The lengths of covalent bonds tend to be shorter than the ionic bonds because there's orbital overlap. Like this orbital overlap, like two circles. Say this was a hydrogen, one of the hydrogens, and this is the other hydrogen. There's an overlap right here. There's orbital overlap. Let me call it orbital overlap. And where this orbital overlap, that's where the bond is formed. That's where the two shared electrons will be to give you H bond H. And that reduces the distance from nucleus to nucleus because the circles are coming closer. Hydrogen and hydrogens tend to be very small. HH, they are small. So you'll expect that their overlap will be very effective and the distance is going to be shorter, roughly 74 picometers. But if you take a hydrogen, a baby, and then overlap it with something bigger, an iodine, the internuclear distance will increase, which is why you see it to be 161. Okay, because of the size of iodine, the pink size, the pink side, this is the iodine, and this side is gonna be your hydrogen. So depending on the sizes of the atoms, you expect the internuclear distance, because the nucleus of the atoms are right in the center, the internuclear distance or radii or radius will be longer, or even you could say the bond is gonna be longer because you're looking at the bond length, which is the distance between the two nuclei where there's overlapping. So you are shown here the bond lengths. CH is 107 because hydrogen is a baby. But now if you look at bigger elements, I'm trying to look for bigger elements here. Oh yeah, you can look at nitrogen and oxygen. You see, look at the bond length is 136. However, compare N single bond O and double bond O. Whenever you have double bond, the bond tends to be stronger and shorter. It's like me telling you to break one pen versus breaking two pens. Breaking two pens will require more energy. So there's more overlap in making a double bond, and the bond becomes more stronger. And you see the bond length decreases, and it even decreases more if you have a triple bond, and that could be better explained when you're looking at NN. So this is N single bond N, N double bond N. Look at the bond length. It's decreasing as you go up to the triple bond. So that's what we call bond order. The bond order here is 1. The bond order here is 2. The bond order here is 3 for nitrogen gas. So you can say increase in bond order equals to decrease in bond length. It's the same thing with oxygen single bond. Gives you bond length of 148 picometers, but oxygen double bond gives you 121. Same idea. Here bond order is 1, here bond order is 2 because of the double bond. Increase in bond order equals to decrease in bond length because of effective overlap. So generally, bond lengths, the triple bond is gonna be shorter than the double bond, and the double bond is going to be shorter than the single bond, which is the information that you see here. If you are ever asked to rank, use that information. Let us now compare ionic compound to molecular compound. What is a molecular compound? It's made of nonmetals. Okay. What is an ionic compound? It's made of a metal plus a non-metal. Alright, so comparison of some general properties of an ionic compound versus a covalent compound. Sodium chloride itself is white solid. Carbon tetrachloride is a colorless liquid. This is a solid because the forces involved here are intramolecular. The intramolecular forces are strong, and it turns out to be ionic electrostatic forces, while here the we don't talk about intra, we talk about intermolecular, the forces between two molecules. They are weaker, so you expect carbon tetrachloride to be a liquid, while sodium chloride will be a solid because it has strong ionic intramolecular forces. And those strong ionic intramolecular forces causes the melting point of sodium chloride, an ionic compound, to be very high compared to carbon tetrachloride, which has negative 23, while sodium chloride has 801. The heat of fusion here, as marked with an asterisk, okay, are the amounts of heat needed to melt 1 mole of the solid and to vaporize 1 mole of the liquid if it's vaporization. So for you to melt 1 mole of sodium chloride, that's the much kilojoules you need, but for carbon tetrachloride is less. And the same idea will be used for boiling point. Because of ionic bonding, which are stronger, it's difficult to boil off sodium chloride, but it's easier to boil off carbon tetrachloride because all that you have there, the intermolecular forces between the carbon tetrachloride, is actually some dipole, which is weaker than sodium chloride. All right, same story for heat of vaporization. You're just focusing on a strong ionic bonding versus the dipole. Density. Sodium chloride tends to be more dense than carbon tetrachloride, again because of how compact the ions are in the crystal lattice. Solubility. Sodium chloride, because of the charges in Na plus and Cl minus, this is polar, but solubility of carbon tetrachloride in water is going to be very low because carbon tetrachloride, CCl4, is really nonpolar. The dipole moments cancel out. Let me talk about dipole moments. We know that electronegativity here is higher for chlorine than carbon. So you're looking at a structure that looks like this generally. Those are dipole moments, and they're canceling out left and right. So overall, there's no dipole, making carbon tetrachloride nonpolar. The principle of solubility is like dissolves like. Birds of the same feather flock together. So you don't expect nonpolar carbon tetrachloride to dissolve in the polar water. Water is polar. There's contribution of dipole moments. Water and sodium chloride, it works. They dissolve each other. You put salt, table salt in water, it just disappears by dissolving. But carbon tetrachloride, you'll see 2 layers as if you're mixing oil and water, because oil itself is nonpolar anyway. Electrical conductivity. When sodium chloride is in solid form, you have no ions, so it will be a poor conductor. But when sodium chloride is in liquid form, you most likely have those freely moving ions, and because of the charges, then it's a good conductor of electricity. Now, like I said, carbon tetrachloride is not ionic, it's covalent. There are no ions, it does not dissociate in solution, so it will never conduct electricity because there are no ions. Let's come back and talk about the covalent bonds, but this time around, let's focus on polarity. When you say something is polar, it means it has the positive end plus the negative end. Like your car battery that you use to start your car, right there inside the trunk of your engine area, you have the cathode side and the anode side, positive and negative. So your battery is polarized. Alternatively, if you look at the magnet, he has the north pole and the south pole. That's kind of a polarization. So a polar covalent bond or polar bond is a covalent bond with greater electron density around one of the 2 atoms that are on the side of the bond. If you look at H and H, which one is more electronegative than the other one? None, because these are same elements. And because they are same elements, I expect this bond right here to be covalent, yes, but nonpolar. So this will be nonpolar covalent. And you can see the distribution where colors are evenly distributed in here. Usually the blue side is supposed to be the positive side, and the orangish, brownish side, that's the side where you should have the negative density. But you can see how even and symmetrical the colors are distributed. Whether you look at it this way or look at it this way, the molecule is not very polarized. In contrast, if you focus on HF, hydrogen fluoride, we talked about the trends in electronegativity. We say that electronegativity increases left to right, down up, fluorine being the most electronegative. Hydrogen is somewhere here. Fluorine is farthest to the right. So we expect polarity to be facing the fluorine, and that will be partially negative while this is partially positive. So that is what you see here in this globular representation or drawing. So the side where you have the orangish, this side, that's where you have high density of electrons or negative charges. So this is the negative side. And then the blue side here, this is where you have high positive presence or density. So this is partially positive, this is partially negative. We don't use full charge plus and minus because we still have these two atoms bonded. So we use this sign sigma to represent partial. Okay, so you have partial positive, this side, the blue side, partial negative, the brown side. And that makes HF, hydrogen fluoride, quite polar. I expect HF to dissolve in water, but I don't expect hydrogen gas to dissolve in water. Electronegativity, we discussed about this in an earlier lecture, is the ability of an atom to attract towards itself the electrons in a chemical bond. And like we said, if you are to compare H and F, F is more electronegative, so the bonding electrons will dwell very close to fluorine than hydrogen, making the fluorine partially negative because electrons are negatively charged. Hydrogen will be partially positive. Electron affinity itself is measurable. Chlorine will have the highest electron affinity, okay, which is just the energy released when an atom absorbs an electron. Take, for example, a fluorine atom in gaseous state. When it gains an electron, it gives you a fluoride, and the resultant heat released, delta H, will be equal to, that is for the electron affinity, is going to be equal to what we saw before here in the lattice energy calculations. Right here, negative 328 kilojoules. Negative 328 kilojoules. We put negative because I told you electron affinity is just the amount of heat energy released when an atom in gaseous states gains an electron. And so we can generally say an element in gaseous state gaining an electron will give you an anion in the same gaseous state, releasing some heat. Electronegativity, which is the ability of an atom, of an element to attract electrons towards itself, increases from left to right, and also is going to increase generally from bottom to top. Usually fluorine is the most electronegative element generally in the periodic table, and you're given here some values. This table that has those small numbers, those are not atomic numbers, they are not mass numbers. Those are Pauling scale electronegativity values. Okay, so the higher the number, the higher the electronegativity En. Okay, that increases from left to right, and then bottom to top. Fluorine is the most. Now, using these numbers in the periodic table here that are usually provided to you, or you print them if you're taking the class online, you can print them and bring them to your exam desk. You can print this page alongside the periodic table, bring it to your exam desk. You can use these numbers to determine if a bond is non-polar covalent, polar covalent, or ionic. All right, so this table that you're looking at here, the variation of electronegativity with atomic number, is just showing you the trend. Y-axis here is the electronegativity. It increases as you leave the metals going to the non-metal. As you leave the metal, okay, lithium is a metal, so let me write here, as you move from the metal to the non-metal, the chlorine here is a non-metal. So you see, lithium is right here on the left, fluorine is right there on the right, sodium is right here on the left, chlorine is right there on the right. So generally, you expect that the nonmetals will have higher electronegativity than their metal counterparts in the same period of the periodic table. So if K is here, bromine is there, I expect that bromine is going to be more electronegative than potassium, the K. Again, iodine, the nonmetal, is in the same period as rubidium. Iodine is going to be more electronegative. So you're looking at the trends here, right? Now, like I said, you can use the Pauling scale to determine if a bond between two atoms is polar covalent, non-polar covalent, or ionic. Okay, so when it's non-polar covalent, people usually just call that pure covalent. The difference in your Pauling scale numbers is most likely going to be 0.5 or less. That is for the difference in electronegativity that will help you to judge that the bond is non-polar covalent, or what other people call pure covalent. Now, if it's ionic, the difference in electronegativity between the two atoms must be greater than or equal to 2. If it's polar covalent, it should be anywhere between 0.5 and 2. Okay, I've done some corrections here, so you'll need to note this down and write them down. Okay, so let's do an example. CH. We are going to refer to a Pauling scale table, which I said you should print if you're taking this online and have it with you. Carbon has Pauling scale value of 2.6, is right there. Hydrogen is 2.2. So let's see the difference in electronegativity between CH. So it will be 2.6 minus 2.2, I get 0.4. 0.4 is definitely less than 0.5, which means this bond right here is non-polar covalent. Okay, now let's look at the case of sodium chloride. What is the Pauling scale of sodium? Sodium is 0.9, chlorine is 3.2. So come here and say sodium is 0.9, chlorine is 3.2. So I'll do bigger number minus smaller number always. You don't want to get a negative answer, and this gives you 2.3. 2.3 is greater than a difference in electronegativity of 2, so this one is going to be judged ionic. So our example here is going to be sodium chloride. The example here is a CH bond, I said. And now let's look at polar covalent. Let's assume you have water. Look at this bond, hydrogen and oxygen. Go to the Pauling scale table. It says 3.4. You don't need to memorize these numbers. I said you have to print this table. So oxygen is 3.4, hydrogen is 2.2. I subtract the smaller number from the bigger number. 3.4, 2.2, 3.4 minus 2.2, the answer is 1.2. 1.2 lies between the 0.5 we corrected here and 2. So this bond right here is polar and is covalent because of sharing of electrons. Now remember that covalent bonds are made by sharing. Electrons, ionic bonds, are made by complete electron transfer. We did examples of this. Okay. So this is just showing you percent ionic character. And you see these guys down here, they are covalent. With very less electronegativity difference, they're going to be covalent. But those that have high electronegativity difference, they tend to be ionic, because we are going this way. Okay. And this will have high ionic character. That's what this small graph is showing. Classify the following as ionic, polar covalent, or covalent. So we are looking at the first case is H and Cl. We determined that H is 2.2. The Cl was 3.2, if I'm not wrong. Yep. Just use the Pauling scale table. Difference in electronegativity, which is the electron pull ability of an atom, will be 3.2, bigger number minus smaller number. It gives me 1.0. 1.0 is right between 0.5 and 2. Actually, the book is quoting 0.3. That is an error. It's supposed to be 0.5. Okay, so 0.5 and 2. So that makes this bond polar, and it's covalent because I have two nonmetals, hydrogen and chlorine, so I'm getting sharing here. Next is K and F. I know that the F has the highest Pauling scale of 4. Let's look at it. Yeah, fluorine has 4, potassium has 0.8. All right, simple subtraction. 4 minus 0.8. 4 for the fluorine, 0.8 for the K. This gives us 3.2. 3.2 is definitely greater than 2. So we expect that KF is going to be ionic. So verdict, this is ionic. Now, in this structure, if I draw it out, it's going to look like this. Trying to draw the Lewis structure of this formula. And they want us to find the properties of this CC bond, if it's ionic, non-polar covalent, or polar covalent. Now, carbon, we said it was 2.6. If you look at the Pauling scale, carbon has a number 2.6. So delta En of the carbon and carbon will be 2.6 minus 2.6. That's going to be 0. I expect that to be non-polar, and it's going to be covalent. So that's how you do such questions.